Well, thanks everyone for coming. Today we've got two talks, one by Professor Junwang Tang at UCL and one by Junwang at the University of Kent. Just to introduce Professor Tang, so he's a professor in the Department of Chemical Engineering at UCL, as you can see in the background from his video. And they'll both be talking about their flexibly funded projects through the UKCCSRC. Junwang's main work is around photocatalysis rather. So if I can leave the stage open to you, Junwang.
Thank you. Shall I start sharing my screen or?
Yeah, do you want to go ahead?
Thank you. Okay, so first, thanks to the UKCCSRC giving me a chance to share the research results achieved in my group on the CO2 conversion. Oops, 1 second, let me see if I can find my laser point. Yes, okay. Before moving to the results, let me introduce what's photocatalysis. You can see photocatalysis can split the two words. The first one is a photon, and second is catalysis. So we try to use a photon as energy to drive a chemical reaction. Now, what's the best source for photon is solar energy. Apart from solar, we can use artificial source, prefer solar energy because that's abundant and relatively low cost. Now here, the focus is a solid material called a semiconductor catalyst. And that one can absorb sunlight and convert that photon to a pair of charge carrier, electron and hole. And then we use this pair of charge carrier to drive different chemical process. The first one, people, you already know that one, is to split water, reduce protein to hydrogen, and then oxidize water to oxygen gas. So finish the full cycle, we produce hydrogen fuel. Alternatively, we also can use the electron to reduce CO2, either to carbon monoxide or alcohols. And the other half reaction is use the positive charge hole to oxidize water, get oxygen gas, and then we finish the cycle. Now, from here, what we can learn is that two key issues we have to solve. One is efficiency. We need a high efficiency, in that case, we need a good catalyst, photocatalyst here, and also we need to control the selectivity. So for CO2 reduction, we can reduce CO2 CO or maybe a methanol, ethanol, or which one we prefer, and that's related to the selectivity. So we have to work on both high efficiency and high selectivity. So in my group, we work on this photocatalytic addition of small molecules. The first molecule we are interested in water splitting to produce hydrogen gas, as just mentioned. And the second is CO2 addition to either chemicals or fuels, liquid fuel. The third one is to convert natural gas to ammonia, because this is currently is a bigger CO2 emitter in industry. And last one is to activate the small organic molecules, methane, to high value chemicals. In parallel, we use this spectroscopy. One is time result spectroscopy, observe charge dynamics all the way to nanosecond to seconds. The second is use this not spectroscopy, which is time result. Sorry, is intensity modulator photocurrent and the photovoltage spectrum to observe charge kinetics. So we can observe charge dynamics and reaction kinetics. Another separate in my group, which is a microcatalysis to decompose the polymer to the monomer and reuse this monomer. So today my talk will focus on the CO2 conversion. We read news every day, somewhere maybe it's flooding, and the other side world maybe is very, dry. And we also see last week that news on BBC again talk about the climate change. Now, if you're interested, recently I just bought this book. It's quite interesting. This book uses lay language, tell us about the consequence of CO2 emission and what's a possible solution. Written by Bill Gates. It's quite interesting things. As one said, the other said, there's one paper published last year. Authors, I think, invested maybe 6 sets in China and across 7 years. What have they found? 45% CO2 in air already utilized by nature, by either forestry or the crop, which is interesting news. Now, what we can learn from here, it seems to me that 2 points I have to pay attention. One is nature does need CO2. So when we want take a CO2 from air, we need to think about how much CO2 we have to left there for nature photosynthesis. And then second interesting thing is if we try to capture CO2, where we can store the CO2, we may see we can convert the CO2 to inorganic materials such as carbonate, whatever, or you can convert the CO2 to the organic molecules. So which one we prefer? Think about carbon. If carbon is a very valuable feedstock, if we take a carbon, convert it to inorganic, we cut off that carbon cycle. So put that way, I personally prefer to convert the CO2 to organic molecules. That's where we can cycle the carbon. Okay, so we'll talk about CCS and the CCU. As just mentioned, I personally work on the CCU, I like the CCU. Our next question is, what molecules we want to convert CO2 to? Yeah, that's also related to the selectivity of CO2 conversion. We can convert CO2 to carbon monoxide, we can convert CO2 to formic acid or methanol and methane. Think about if we want to convert CO2 to organic molecules, we do need protein source. Now, what's the best protein source or the cheapest abundant protein source is water. And therefore, we have to think about how to activate both water molecules and the CO2 molecules in order to get organic molecule. Now, look at the chemical bonds in water, hydrogen-oxygen bonds. The energy required to break the bond is very large, 459 kJ per mole. And the carbon-oxygen double bond near 800 kJ per mole. So you can see both process is very challenging. That's why we need clean, renewable energy to do the chemical process, otherwise we may end up with more CO2 emitting. Now, what's a renewable energy source we want to use to activate both water and CO2 molecules? And I think solar is the best solution because it seems the amount reaching the surface of the Earth is 10 to 5 terawatt, and over the last few years, average year, we consumed overall 13 or 15 terawatts. So it's nearly 10,000 more than we need. That's, I think, is the best solution to activate these two molecules. And also the good news over the last few years, you can see the utilization efficiency of this fuel, whatever fuel, dramatic increase. So you can see the keep increase with time. Now, the other two figure is quite interesting for me. Now, look at this one. X-axis is the energy content per ton carbon, or that's the other way is energy stored in the chemicals. You can see from X-axis. Therefore, if one comes CO2 to a useful material, we prefer the left side, sorry, right side, because more energy stored inside. And look, so the other one, Y-axis, that is a market price per ton of carbon. Clearly, if you want to make profits by the CO2 conversion, we prefer products top half, because that can give us more profits. Therefore, this corner should be the best product we should target. Now, this dotted line tells us the energy cost. If we want to use electricity convert CO2, what's the current price of electricity on average? Roughly 60 and 60. Now, its dotted line is 50, very close to $50 per megawatt hour. So that's current price of electricity. If you use that one, we have to produce something more valuable than the electricity used. So that again tells us we have to focus on this product. Now, in future, we may use wind or whatever, so to reduce this electricity price to $20 per megawatt hour. But still, similar conclusion suggestion is we have to produce the products at this corner. That's the reason if one consider selectivity of CO2 conversion, we have to think the product must be methanol or carbon too, not methane, not CO, not syngas, because either energy source is too small or the price is later, maybe cannot compensate the cost of electricity. Okay, so photocatalysis is not a new concept. That developed 40 years ago. And what's the challenge in facing that area? We spent quite a long time to understand why the solar to fuel conversion is still very moderate. I take one example here. We first observed the charge generation and recombination in TL2, which is a very popular photocatalyst. Now this red curve is a fingerprint of a positive charge hole, and the black is the electron. We observe all the way from nanosecond to second what happened between these two charges. We saw very identical decay curve. That indicates this one reflects the recombination of charge carrier or reaction between hole and electron. If we go further, analyze this curve, what we can find at this time scale, which is the microsecond time scale, nearly 50% of the charge carrier already disappeared. Now, if you want to use this charge carrier to drive chemical process, and this chemical process is a bit slower than this time scale, we cannot get a high efficiency. Now, we observed water splitting because that is a half reaction for CO2 reduction, oxide water. Now, next red curve is exactly the reaction between the positive charge hole and water. Now, if you fit this one to the first order decay, you can get the 50 with the half lifetime is of a charge carrier is about 0.2 seconds. And at the same time, we observed the oxygen gas production. And that proof that this one indicates oxygen production from water. And that's half reaction. If you remember what I just mentioned, the oxidation half reaction is oxide water to get oxygen gas. It's very slow, which is here. And that's why solar to fuel conversion efficiency is very moderate currently. And we further extend our study from TiO2 to other photocatalysts. We end up with a similar, very similar diagram here. So charge generation in a semiconductor, most semiconductors is very fast, is picosecond time scale. It looks at hydrogen production half reaction, which is here. It's okay, it's microsecond time scale. And looks at charge recombination against the microsecond time scale. It's compatible between the two. However, the other half reaction, oxygen production, is second time scale. It's very slow. Now, talk about the CO2 reduction. We're not yet known the time scale for CO2 reduction. Now, if we take this one example, this is a 2-electron process. This is a 6-electron process. Very likely it's slower than it. And this one, why is very slow? We change the numbers of photons per nanoparticle per catalyst. What we observed, just at 4 photons per nanoparticle, we get the highest oxygen evolution rate, and the second peak of 12, and third, sorry, second is 8, and the third shoulder peak is 12. That indicates if you want to get highest oxygen evolution rates, we have to have a multiple of 4 of photons. So that's give us the reason why this one is very slow, because kinetically, we need a 4 hole come together oxygen water to get 1 molecule oxygen. That's very slow. Now take this one example, further proof CO2 reduction, such as to the methanol that we just discussed, the preferred product. As a 6-electron process, should be slower, much slower than this one. Now, if we want to use the photon-driven CO2 reduction by photocatalysis, we have to solve the 2 challenging things. One is slow down the charge recombination, and second, we need to speed up both the reduction and oxidation reaction. Okay, so what we did first is to prove, can we use photocatalysis to drive CO2 reduction? And here we use a well-known photocatalyst, which is cube oxide. The reason we pick up this one, that's because this cube oxide have a narrow band gap, can absorb more photon from solar spectrum, and the conduction band is quite negative, which is enough to reduce CO2, and also cost relatively low, and then naturally it's a p-type semiconductor that prove the mobility of a hole inside very fast. However, we cannot use the cube oxide for the reduction and oxidation because the hole in the valence band is too negative to oxide water. So here we just observe the half reaction, CO2 reduction. Okay, the other part is not oxide water, it's oxide sulfate. Now the control experiment tells us if we don't have water, we don't have CO2, we don't have a catalyst, we don't have a lighter, there isn't any CO produced. Now when we use a cube oxide photocatalyst, we can observe CO produced. And when we add a co-catalyst on top, that can speed up the oxidation reaction. We get high activity. However, after roughly 1 hour, the activity rate dramatically reduced. And then we observe the catalyst, the photocatalyst here. Next is our original photocatalyst surface. And after 3 hours, see the surface more or less porous structure. The reason for that is because the photocorrosion. So the photon can oxidize the cube oxide itself to copper oxide. That causes a photocorrosion process. Now we put cube oxide, ruthenium oxide on the cube oxide, we get this surface photocorrosion reduced, but we still can see some damaged surface. Now, next step, we try to further protect this cube oxide from photocorrosion by adding a surface layer, which is graphene oxide. And as a material, we prepare the cube oxide on top of this thin layer. It looks very good, it's a very ugly surface, and that's easy graphene oxide. And then what we observed here, when we add the graphene oxide on the surface of cube oxide, activity dramatically increased compared to the cube oxide itself. So activity increased nearly 10 times. And that's just the optimization process to change the ratio of graphene oxide to the cube oxide. Now, if we compare our best optimized graphene oxide, cube oxide catalyst with TL2, P25, you can see the materials give much better activity than P25. Because we add the graphene oxides on the surface cube oxide, that is kind of carbon source. We have to prove our products is from carbon dioxide, not this impurity, not graphene oxide. That's why we did this as top environment. When we use carbon-13 dioxide as a feedstock, we get these products with a mass 29, as I can prove our CO carbon monoxide from carbon dioxide. So let's prove we can convert the CO2 to some products, reduction products such as carbon monoxide. However, it's a half reaction. We prove the feasibility, but it's not ideal process. Now, next, what we try to do is use water to reduce CO2. In that case, you can see is oxide water and reduce CO2. And we also prefer to generate methanol instead of carbon monoxide, because as we discussed, methanol is a preferred product. And here we use a catalyst as a polymer, which causes a carbon nitrate, carbon-3 nitrogen 4. You can see here, that is a carbon, and that's a nitrogen. So we have in one ring, we have 3 carbon. Overall, we have, I think, 6 carbon and 8 nitrogen. That's what got the ratio, carbon-3 nitrogen 4 here. Catalyst is a very good polymer for the catalyst, quite stable. However, as we just mentioned, we also have to speed up water oxidation. Therefore, we have added something on top of this to speed up water oxidation. Otherwise, we cannot use water as a protein source to reduce CO2. Okay, what we did, we prepared another called a co-catalyst with carbon dots and add that on the surface of a carbon nitrate. Now that's our carbon nitrate surface. And there are small spots, that is our carbon dots, roughly is 2 nanometers in diameter. And this carbon dots prepared by microwave, that's the way I see here. M is indicate the carbon dots prepared by microwave. And we also prepare the carbon dots by the conventional method, which is a chemical reaction. Okay, when we look at this carbon dots on the carbon nitrate, see this picture here, and further we zoom this one, that is the lattice is carbon nitrate, and this lattice is carbon dots. So we clearly see the carbon dots on the carbon nitrate. Okay, now we also loaded this one, the conventional carbon dots on the carbon nitrate. And we have 2 photocatalysts. One is microwave prepared carbon dots on the carbon nitrate. The other is conventional carbon dots on the carbon nitrate. And that's our polymer carbon nitrate. You see the absorption, this carbon dots increase absorption a bit. And more important is activity for CO2 conversion. When we use the microwave carbon dots on carbon nitrate, we can reduce CO2 to methanol. And the other byproduct, carbon monoxide, nearly 0. That proves we have very good selectivity to the methanol, nearly 100%. And oxidation product, which is oxygen gas. And if you work out the ratio is 2, you get exact ideal ratio 2 to 1. Sorry, 3 to 2, 1.5 to 1. That's ideal ratio for this reduction and oxidation reaction. Now let's use our microwave carbon nitrate. If we use a conventional carbon nitrate on conventional carbon dots on carbon nitrate, the major products is carbon monoxide, not the methanol. You can see the co-catalyst here is carbon dots play a big role. It can change the selectivity from methanol to the carbon monoxide. And also interesting things is the reduction rates when you use this conventional carbon dots is relatively low. And if you look at this one, it's nearly 20 times higher than that. A unit is same, your micromole per gram catalyst. And then here, summarize, if we just use the carbon dots, no matter it's micro prepared or the conventional method as no CO2 conversion. When we use the carbon nitrate itself as a photocatalyst to convert CO2, unfortunately, there's no CO2 reduction take place. When we use our carbon dots on top of carbon nitrate, we get a very good CO2 reduction to methanol. And the other conventional carbon dots give us carbon monoxide, not methanol. So you can see the conversion rate different and the selectivity different. Now we try to understand why there's such difference. And this just tells us the process to optimize the ratio of carbon dots to carbon nitrate. From the best ratio is here, 3.5% with the percentage of carbon dots on carbon nitrate. And also we test the stability of the catalyst, seems quite well. Over 12 hours, get a linear increase of methanol. Again, carbon monoxide amount is very, very small. That's why you see here, we zoom this one, can see that. Otherwise, in the same figure, we cannot see the production rate of carbon monoxide. Further, we prove our products is from carbon dioxide because catalyst and co-catalyst both composed of carbon. That's why I have proof in the final product what's a carbon source. When you use the carbon-13 CO2, we get the products again proof that's carbon-13 methanol. And this is the quantum yield measurement. See at a visible region, we got something like a 2.1% of photon was used to drive this chemical process, CO2 reduction. Again, repeat this 3 times, gets a very good reproducibility. And next step is to understand fundamentally what's the difference between our microwave carbon dots and conventional carbon dots. We can see, if you recall what I just mentioned, the fingerprint of the electron, we can observe that long wavelength 700 nanometer and the positive charge hole as 500 nanometer, 510 nanometer. Now, when we observe the charge dynamic of the hole on the carbon nitrate with our carbon dots, we add a silver ions as an electron scavenger. We see the increase the signal. That proof, yes, this is a fingerprint of a positive charge hole, and dramatically reduce the signal when we observe 700 nanometer. That proof is electron signal. And next, we observe the difference between the two photocatalysts. So that 700 is signal of electron, which is marked here. And we see that's a very good signal on the carbon nitrate. When we add a silver ions, and that may reduce because silver ions can react with electrons and take electron away. That's because of electron scavenger. When we add the carbon dots, the microwave carbon dots, we see the signal of electron increase, as indicated very likely positive charge transfer from carbon nitrate to carbon dots. Therefore, the electron on carbon nitrate dramatically increase the electron signal. And in this case, you add a silver ions, again, this one disappear. And I prove, yes, very likely whole transfer from here to there as well. Electron on carbon nitrate signal dramatically increase. Now, conventional carbon dots show different process. You see the electron signal dramatically reduced. When I add the silver ions as no change, that proof very likely after excitation, electron transfer from here to there. Therefore, electron signal on carbon nitrate doesn't increase when I add the conventional carbon dots. And this is further proof our microwave carbon dots can dramatically increase the photocurrent, again, as because the charge transfer. Now here give us an diagram. After excitation, an electron very likely to reduce CO2 to methanol, and then whole transfer from carbon nitrate to our co-catalyst microwave prepared carbon dots. And then on top of that one, water can oxide to oxygen gas. Now, conventional carbon dots play a different role. That's attractive electron. Yes.
If I could ask you to proceed to conclusions, just so we can get time for questions.
Okay, thank you. So that's just a model results prove the similar things, and then we end to the last slide. That is exactly what I mentioned as a previous the reduction of electron reduce CO2 to methanol use a protein from water, and the whole transfer to carbon dots oxide water to oxygen gas. And that's end up as a last slide is a conclusion. So we observed the fast charge recombination on the photocatalyst, and then we proved the possibility of CO2 reduction by cube oxide, even though it's a half reaction, and that photocatalyst can do CO2 reduction. And then we developed another photocatalyst, which is carbon dots on the carbon nitrate, and that can reduce CO2 by water to methanol, and nearly 100% selectivity to methanol. And the reason for that is because the function of these carbon dots. That's help charge separation and also oxide water to oxygen gas. Now, I should thank the majority of the members in my group. I don't have time to speak of them. And then thanks the collaborator from Imperial College in Hong Kong U and Canada. And also thanks the funding support from the UKCCS and other funding body. Thank you. Yeah, that's the last slide.
Thank you very much, Junwang. I think we've got time for just a couple of questions. We'll maybe come back to it later. So if I could invite anyone who has any questions just to unmute. I guess just to get us started, what's the manufacturing process for the microwave manufactured carbon dots? How scalable is that as a process?
What we did, we used urea as a carbon source, and then we add another, I think it's formic acid. The reaction between these two driven by the microwave energy, which is a very fast process. Just mix the two precursors together, put in microwave, and switch on microwave for I think it's about 20 minutes, and it gets the small spots precipitated in the solution. And then separate that one. That is a micro carbon dots. And then when we get to the carbon dots, we load the carbon dots on the carbon nitrate by a very simple impregnation method.
Okay, thank you. Are there any other questions? Maybe we'll take one at this point, then we'll move on to Professor Yang's talk.
Yeah, I can see the one question is from Fari about the whole scalable of this method to industrial, I guess, is a large scale. Now, the carbon nitrate preparation method is well known, which can be scaled up, and carbon dots, I think we can scale up that one because it's a very fast process. If the macro power is big enough, we can produce the carbon dots maybe kilogram, and then we can load that on the carbon nitrate to make the photocatalyst. That's about the scale up of the catalyst. Scale up the whole system, including the CO2 reduction by water, not require energy source. If we use artificial light source, that's easy. We can scale up and work for 24 hours a day. If we use sunlight, maybe just a half day work.
Thank you very much. So that was my question. So follow up to my question. So what about the price for industrial use, let's say? Is it something that is possible to pay, let's say, in terms of industry? And do you have any estimation? Yeah. Thank you.
Thanks. And that's a very challenging question. I don't have that's a value in my mind because it's very difficult to estimate that one currently. All the scale we currently work is in laboratory, very small scale.
If I could pause that there then, thank Professor Tang again for the talk. And if we have time, we can come back to it later.